Okay, lads, I'm going to go through some derivative differentiation by first principles. So this is how deriving functions first kind of was proved. So what does the derivative mean exactly? So the derivative, how the function changes. So the derivative is just telling us how the function changes. So if this was a function of, I don't know what this could be. This could be just a ball flying through the air. So this could be its arc through the air, for instance. I want to know how it's changing at each point. Most things in the world are changing, right? Well, everything is changing. And so it's really a huge area of maths is to know how things are changing and then make predictions. Obviously something at the moment is happening in the world, and there's probably a lot of people interested in how the trends are changing. So this sort of mathematics can be applied to the weather, to the stock market is a huge one, the housing market, fluid motion, a lot of physics. I could go on and on. So what we want to do is we want to look at the derivative of these three functions by first principles. So first of all, we start with the notation f prime of x. So that's the first derivative. Now that is equal to the limit of the following function as h goes to 0. So I'll just write that in first. It's equal to the limit of f of x plus h, take away f of x, all over h. So the derivative is the limit of f of x plus h minus f of x divided by h as h goes to 0. So we're interested in what is happening to this function as h goes to 0. So let's have a look at what that might look like. So if we have f of x plus h, well, that's going to be x plus h squared. So all I have to do is put x plus h in for whatever my input variable is. So x becomes x plus h. So it's x plus h squared plus 5 times x plus h. And then we're just taking away the original function. So we take away x squared, take away 5x, all over h. Looks like I'm going to kill some room on that problem if I'm not careful. So now we expand and simplify. And I need to make sure, I always forget this, that I'm always taking the limit of this thing as h goes to 0. So this equals the limit as h goes to 0 of x squared plus 2xh plus h squared, just expanding that, plus 5x plus 5h, take away x squared, take away 5x, all over h. And then this is quite a pattern. We always get these sort of things cancelling down. We are left with the limit as h tends to 0 of 2xh plus h squared plus 5h all over h. So I've got those three terms left. Now I can divide by h. So h is going to cancel top and bottom. And I'm now taking the limit as h tends to 0 of 2x plus h plus 5. So what happens as h goes to 0 of 2x? Well, it doesn't depend on h at all, so it stays right where it is. What happens to h as h goes to 0? As this thing gets smaller and smaller, well, that's just going to vanish, so it's gone. And what happens to 5? Well, 5 is just a constant. It's not dependent on h at all, so it stays there. And there we have it. We have now derived x squared plus 5x by first principles. Cool. So you could give this one a go yourself before I whip through the answers. So f prime of x, so I just finished that one off there. F prime of x is 2x plus 5. F prime of x is the limit as h tends to 0 of this function of f of x plus h minus f of x. So that's just, remember that's the difference in y. And then what happens if we make that difference go really, really small, because that's a difference in x. What happens if we make that smaller and smaller? We're going to get an actual gradient for that function. So it's going to be equal to the limit as h tends to 0 of 3 times x plus h squared. So notice it's just that function, but their input now is x plus h. Take away the function, where just x is the input, over the difference in x, so over some h. Let's take the limit. We're always taking a limit all the way down, so I write it every time. Expand and simplify the top. 3x squared plus 6xh plus 3h squared. Take away 3x squared all over h. Okay, so now we'll do some cancelling. So that's going to cancel with that, and we're left with the limit as h gets closer to 0 of 6xh plus 3h squared all over h. That h and that h will cancel, because h divided by h is 1, and h squared over h just leaves an h. So we're left with the limit as h tends to 0 of 6x plus 3h. Now what happens as h gets close to 0? What's going to happen to 6x? Well, it doesn't depend on h at all. So it stays where it is. And what happens to 3h as h goes to 0? Well, let's try it. So when h is 1, it's 3. And then let's let h go to a half, well, it's 1.5. And let's let h go to 0.1, and we're left with 0.3. And what you can see is that's just going to go, and it's just going to vanish as h gets closer, infinitely close to 0. So does this. And so we're left with 6x. So f prime of x is equal to 6x. That is our gradient function. So now we've got our original function. This function will tell us what is happening at every point, no matter if we plug it in. Okay, last one. We're going to go a little bit more abstract. I've just got some constant out the front. Let's have a look at what's going to happen. Well, the gradient function is the limit as h goes to 0 of f of x plus h squared. F of x plus h minus f of x all over h. So this is going to be the limit as h goes to 0 of ax squared plus axh plus 2axh. So I'm going to get x times h plus h times x. So I get 2xh times by a, so 2axh plus ah squared, take away ax squared all over h. Those ones will cancel out. I'm left with the limit as h goes to 0 of 2axh plus ah squared all over h. And now my h's I cancel down. So that h and that h will cancel, and one of those h's will cancel. I'm now taking the limit as h goes to 0 of 2ax plus ah. What happens is this as h goes to 0? Well, it stays there. It's not dependent on h at all. And what happens to this as h goes to 0? Well, that's going to be some constant times 0, so it's gone. And there we have it. That is our derivative. So there is a pattern here. So in lower level calculus, you were just told what is happening. So let's have a look at what is the pattern. So we've got the derivatives of these things. So we've got f prime of x is 2x plus 5. F prime of x is 6x. And f prime of x for this one was 2ax. So let's have a look at the pattern. So is there a quicker way than first principles to get from this function to this function. So we want to look at a pattern. How can I get from x squared to 2x? Well, you might notice that we can bring that 2 down the front and then reduce the power by 1. Okay, so that works there. Let's try it again. If I bring that power down the front, then that's going to be 2 times 3 and then reduce the power. So it looks like we've got a pattern. If I bring that power down the front, I've got 2ax reduce the power. So now what we can do is polynomial differentiation. I probably should have looked up the definition of a polynomial, but a polynomial is basically any function that's just powers of x, powers and coefficients of x. So a pretty standard one is ax squared plus bx plus c, the quadratic. It's just a polynomial. This thing here, that's just some polynomial, so it's just some linear combination of powers of x and coefficients. So poly means many, okay, and nomial, I think something to do with numbers, so many numbers, something like that. So what we can see here is that if I have f of x equals 3x squared plus 2x plus 1, we have 3 powers of x. So let's have a look at what's going to happen here. If I want to take f prime of x, we could easily go through the big formula of first principles like we've just done, but we've noticed a pattern. I can bring that 2 down the front, use a different colour. That 2 comes down the front, so we've got 2 times 3x and then reduce the power. So the power comes down by 1. Same thing here. We could have, there's power of 1 on that. So it's 1 times 2x. And what happens when we reduce the power? Well, it goes to 0. And then the constants are a little trickier because they're x to 0, aren't they? And you can't really go to -1 for the gradient. But if you had a line of x equals 1, or any constant, this is just some constant, y equals constant, what's its gradient? Well, its gradient is 0. So any constant goes to 0. So let's have a look at what this looks like. F prime of x equals 2 times 3 plus, now anything to 0 is 1, so that's just going to go 2. So that might have been a little confusing. I'll do another example. So basically bring the power down the front, multiply by the power, reduce the power. So if we were to write that as a rule, if we have f of x equals ax to the n, f prime of x is equal to n, let's write alphabetically, a n x to the n minus 1. That is your rule. So I'll do one more example. Let's have a look at, I think I might have gone out of the camera shot there. Let's have a look at one more example just over here. Let's go f of x is equal to, let's go 4x cubed plus 2x squared plus 3x plus 7. Well, f prime of x is times by the 3. Right, the x reduces power by 1. So that's going to go 12x squared. Bring the 2 down the front. So 2 times 2 is 4. X, reduce the power. When we reduce the power to 1, we don't write the 1. And then this is, if you look at this like, that's a straight line, isn't it? Y equals mx plus c. Well, the gradient of that thing is just 3. So if it's ever just a power of 1, it's just, we just take the number out the front. Because if you reduce the power of 1, you get to 0, so you just get a 3. And there you have it. It's a nice, quick, easy example of finding the derivative of a polynomial. And that was proven to you by first principles and then noticing that pattern. There we go.